We'll start with Vedant, and then he'll take us in a journey back in time, and then we'll come back to where we have started, like which is generative AI. Why do I need a probability distribution?
Sold my old home and I sold it, let's say at some number, $100,000, right?
Mhm.
If I went to my model and I went to some model, which is a square footage of my apartment, and the model predicted $80,000, should I be extremely happy or should I be not surprised? Everyone could have done this 40, 50 years ago. Why is it only interesting now? Is it because deep neural nets are around that I can do something like this?
So if the temperature is 0, will it always give you the same answer? So today is our 16th episode of Generative AI in Enterprise. I started this group back in December 2023, just casually to see like what other people are doing. And then it just kept on going from one episode to another episode. Met so many different people. I met Vivek, I met Vedant, also in this meetup group. So thank you for the continued interest. So today's topic is latent representation of Gen ML models. I'll quickly go through the agenda. So agenda is very simple. So I'll go through it very quickly. So introduction, disclaimer, housekeeping, participant introduction, and the topic of the day, an open floor discussion. Disclaimer over here is all these viewpoints, all the presentation topics, whatever we are doing over here, it has got nothing to do with my employer. This is all opinions of my own, right? This session is being recorded and photographed. It will be shared in social media. So if you have anything confidential, anything IP, you do not want to share your secret sauce, don't share it. So being said, that's it. So we are done over here in the disclaimer. Microphone is like, typically we ask participants to keep the microphones on mute. And so audience intro. So we'll go to a quick audience introduction. Vivek, you want to just add a quick one-liner, Marian, and then I'll ask others also as we go.
Sure. My name is Vivek Sachdeva. I've been working in healthcare and financial services for about 30 plus years. I started out as a software engineer and currently work as a vice president for the project management office.
Awesome. Hey, Marian, if you don't mind to add one line.
Oh, I'm a electrical engineer who's went into patent writing, patent applications, and I'm teaching myself how to build GPTs. I've written several Python chat apps, chat with PDF, chat with images and things like this. So I know how to use them basically, but I also am studying the architecture of the GPTs because I think I'm trying to reduce them, make them very smaller parameters, more effective. So I've been studying the architecture.
Awesome. Okay. Vilagala.
Hi. Yeah. I'm just trying to explore things right now. I have some exposure, but not a whole lot.
Awesome. Anjaya. I think we have met Anjaya earlier.
Yeah, this is Anjay. Yeah, I'm working more about the data, some of the ML space also. Yeah, couple of the LLMs also.
Okay. Satyajit.
Hi, I live in the Princeton area and
Oh, you do? I also live in Princeton area. I'm in Plainsboro.
yeah, okay, not very far. I'm on the other side of one in Bellamede actually. Yeah, and I have just got onto the again on the startup wagon a couple of months ago. So running a 2 months old startup right now. Before this, I've done exit 2007-13. Then I was CEO of a listed company for some time, did some initiatives there. I'm learning my oops in the AI world right now. We'll be doing AI-based solutions for financial services company. That's my current startup.
Awesome. Okay. Fantastic. So we are done over here for our audience intro. So now we'll go to our superstar, Vedant Sachdeva. So Vedant is our guest today. And thank you, Vedant, for your time. So Vedant is a research scientist, PhD biophysics from University of Chicago. Vedant, you love machine learning and you want machine learning to understand and improve biological systems. Worked on novel vaccination strategies, information processing schemas in collaboration with UCLA and ELS Paris. Mission is to leverage skills, expertise in statistics, research, machine learning, a lot more. Actually, a lot more. And the reason I'm saying a lot more, I had a fantastic conversation with Vedant yesterday, and we were just brainstorming the structure of the meetup. And then he was talking so many things. A lot of things was going over my head, to be very frank. I said, Vedant, you need to level it down for all of us to understand. And that's where he said, this is fantastic, but let's have just a casual conversation. Let's go back in the history of time. I know we are all excited about generative AI. We are like building chatbots and reading documents, and every organization is doing that. Every organization is now investing money on building ML solutions and especially generative AI solutions. So now the point is like, where did this all start? So that's where our topic of the day is like, just take a look back and like, where did it all start from? I knew machine learning was only for mathematics and statistics people. How come we are all starting to use it? So in this particular discussion, I'll shut up at this point of time. But in this point of discussion, we'll start with Vedant, and then he'll take us in a journey back in time, and then we'll come back to where we have started, like which is generative AI. So stopping over here, Vedant, floor is all yours. I'll try to collect questions if you have any, and then we can take it forward from there.
Awesome. Yeah, let me just, I'll just share my screen real quick. I already see some questions in the chat about actual coding and implementation of these big generative models. This talk will not be so much focused on the actual coding and mechanical approach to building out these big generative models, but will instead be focused a little bit more on sort of the intuition behind how they work, the math that enables them to work, and how we might actually use the sort of embeddings that these generative models produce to actually pursue and perform certain tasks. So hopefully everyone can see my screen okay and can see this presentation. And I want to start by maybe looking at, when did people really get excited about generative AI? When did it really start to take off in a lot of people in the zeitgeist, right? And I think that
2022, right? December.
Yeah, 22.
ChatGPT came up.
Yeah, just 2 years ago, when everyone realized they could ask a computer a question and get back an answer and have exotic and controversial conversations with these computers that at times felt almost human-like, right? And this is sort of a really, really powerful and interesting technology advance, but for many people, it kind of feels like it came out of left field, right? It was like a brand new thing that is a total surprise to everyone, right? And what I kind of want to show in this conversation is how we can kind of reduce the surprise for ourselves a little bit and intuit what the real technological advance that occurred over the past 10, 12 years that enabled the emergence of this model. And so to kind of understand that, we're going to start by looking at, one of the simplest flavors of models, that is linear regression, something that we've known about for many, many years, and have used, probably many of us have either used or studied at some point during our careers. But I'm going to try and present it from a slightly different approach. I'm going to take a Bayesian approach to it, which I'll introduce as we're going through the conversation. Once we get through that, we'll talk a little bit more. We'll talk about going from regression using linear models to using deep learning models. So how might a deep neural network fit in? How might this kind of thing emerge, right? So for those of you that are sort of familiar, I think, Mar, you had talked a little bit about how can I write up a transformer? How can I write up a GPT or something like this? And not necessarily going to go into the architecture of a GPT, but at least kind of thinking about multi-layer perceptrons and things like this, like what does a deep neural net look like and things of that nature. Once we kind of have a good understanding of how regression works in this sort of Bayesian sense and in this machine learning sense, we can talk about how regression can be extended to give us generativity, to give us generation of new data points. And I'll use that to introduce us to variational autoencoders and also understand how these generative models represent the things they are trained on to produce new examples. If that all sounds good, I'll hop straight into it, and I'll start by there we go, talking about, like I said, linear regression. Now,
basically, you're saying it all started with linear regression.
At the very least, linear regression is a very nice conceptual starting place for most machine learning problems, and I think that probably linear regression is the very first flavor of what people might call machine learning today. And I think many people would call linear regression still machine learning.
Yep. So you're doing a crash course of machine learning of 30 years packed into 30 minutes.
Yeah, I mean, 30 years is probably too short a time frame, but yes.
Or more.
Yeah,
Okay.
absolutely.
Let's
But-
go.
Yeah. So, when we're thinking about these kinds of problems, when we're thinking about regression problems, what we're kind of imagining is that we have some sort of predictor variable of some kind, right? So maybe that's the square footage of a house. And what we'd like to do is we'd like to relate that square footage of the house to the home price, right? Understand how a response variable depends on that predictor variable. Understand how the home price depends on square footage, right? And for the sake of this conversation, what I'll be doing is I'll be referring to a predictor variable as some variable set X, and the response variable as being the thing that we're trying to predict, Y. And the objective of machine learning broadly is to look for relationships between X and Y. So if you're setting out to solve this kind of problem, one thing that you're looking for basically approaches to solve this problem. And a natural approach you might have, given you just plot the data against itself, is like, oh look, these two things look linearly related, right? It looks like almost that X is a linear function, or Y is a linear function of X.
Mhm.
And this might lead you to propose a candidate model that relates the two, right? Maybe you would say, you know what, I'm going to have my prediction of the response variable Y be some function Y hat equal to M times X plus B plus some unexplained noise term. In sort of plain English, what this is to say is like, if I'm trying to predict the price of a house given the square footage, I'm going to say, oh, look, these two things, there's probably some linear function that relates the two things. And I just need to know the slope of that line and the y-intercept of that. And if I can get those two things correct, then I can probably predict the price of my home.
So basically, you're coming up with a function, and you're giving some variables to it, and
Yep.
you're giving some constants to it.
Yep.
And it will predict some answer for it.
Precisely.
Might be close to the expected answer, or
Yes.
might be accurately equal to the expected answer.
Right.
Okay.
We'd like to make sure that answer is as correct as possible. Now, the learning part of this is figuring out what M and B are, right? We know what we get to observe what X is. We get to observe the square footage of a house. And if we have a bunch of data from Zillow or Redfin, we get to see what the prices those homes sold at, right? But we need to see we need to know what the two parameters that actually control the relationship are. That's M and B. And in a machine learning sense, that's basically saying this is what we need to learn. We need to learn what M and B are. And oftentimes you need to choose M and B such something is minimized. When I say something is minimized or something is maximized, what I'm usually talking about is some sense of error, right? I'm looking to minimize the error in my prediction given my choice of M and B.
So minimize the error means I'm closer to my expected answer.
Precisely. And so one way of kind of mathematically like putting that down in an equation or something like that is we're going to say, okay, if I have one example of a home price and its square footage, and I have some prediction Y hat and the true home price Y, then I'm looking to say Y minus Y hat needs to be as small as possible, or the square of Y minus Y hat in this particular case. But we're going to say, like one caveat I'll say is like, we don't just want any single instance to be as close together as possible. We want the average across all of the data to have as small an error as possible.
Mm-hmm.
Cool. So this is kind of gives us a notion of an objective function or something like this that many people have probably heard of in their efforts to optimize a machine learning model or something like this. Now, in the linear regression case, things are so simple that you actually just exactly solve what M and B should be. This is not generally the case for deep learning models or anything like this, but in the linear regression case, you can exactly solve M and B, and I've given the equations here. We could talk about the interpretation of these two in some detail, but I think what I want to convey right now is that your kind of standard approach, 50, 60 years ago, before the advent of deep neural networks or anything like this, to doing machine learning is to do something like this. Propose a model,
Mm-hmm.
choose an error that we'd like to minimize, and then find the right parameters that minimize that error.
Mm-hmm.
Now,
So there is a question over here. If
Yes.
y equal to mx plus b plus error, does that assume that the error is not itself a function of x?
good. So there's an underlying assumption here that the remaining error that is not explained by just the predictor variable is something that belongs to something that is unobserved, right? So when we're talking about the when we're talking about home prices or something like this as a function of square footage, there are many other variables that we're not considering in this conversation that could be used to make that prediction, right? Things like the age of the house, things like the zip code, things like the number of neighboring units or something like this.
So now you're talking about like different dimensions.
Yeah, different dimensions can be.
So maybe like COVID is another factor of home prices going up or down or something.
Correct. Yeah. So these are all things that considered the unobserved. At least, and when you're building a model, you have some things that you cannot observe, you cannot explain, right? And you put that into, and you say epsilon is going to be something that I'm not going to try and model at all, and I'm going to say all my error is attributed to that. That said, it is certainly possible that epsilon can be a function of x, and if epsilon is a function of x, that means that your model is not sufficiently expressive. It is not a good choice of model for the task you're trying to solve, right? So what it means for epsilon to be a function of x is it means there's systematic error in the system, right? You're not making random errors that can't be explained. You're making an error that actually can be explained if you made a better choice. So there's a little bit of a subtlety there. Does that feel like a comfortable? Does that make sense at the very least?
There is a follow-up question. If we instead assume that the error is a function of x, does that lead to y equal to mx plus b plus kx to the power of 2?
Yes. Yeah, that is one possible. That is one possible way of saying, oh yeah, since epsilon was a function of x, I need to add a higher order term in x or something like this. So we now add kx squared or something like this. But unless your data can be perfectly explained by that single variable and you have the exact correct functional model, you're still going to have some error left over, right? And so you always need sort of an error term to keep track of, because unless you have observed all there is to observe about your model and can explain every aspect of it, you may still have some unexplained error left over. And usually you keep track of this number. Right, it's the residual of a prediction or something like this. That's what it might be called in the machine learning literature.
Good,
cool, awesome. So this particular flavor of machine learning is basically, you put in an input and you get back an output. Right, you put in some predictor variable, some set of features, and you get back a prediction based on that model. Right, but maybe what we're interested in is actually another way of framing the same problem is to actually say, you know what, instead of just minimizing some error and saying I want a prediction for every input, I can say that what I'd actually like to do is, given the set of observations that I have, I want to maximize the likelihood of that set of observations, right? So this is to say, like, by clever choice of my M and B, I can say the set of data that I'm observing, the set of home prices I'm observing, given the square footage, is the most likely possible relationship, right? You can call this maximum likelihood estimation or something like this. And if you're looking for sort of a more technical flavor for this. Why is this useful? This is useful because now instead of predicting a single number, you're predicting a probability distribution of possible response variables as a function of your predictor, right? So
I'll ask you a question. I mean,
sure.
Not only for this group, but if someone is looking at the YouTube video also, right? Why do I need a probability distribution?
Good. So I think one useful thing when getting back probability distribution instead of a single output is it lets you know how much you should trust the prediction, or when things differ from your prediction, is that difference unexpected or is it okay? Right. So when we go back to that home price example that I was describing, I recently sold my old home, and I sold it, let's say, at some number, $100,000. Right. If I went to my model and I went to some model, which is a square footage of my apartment. Let's say that was like 820 square feet or something like this. And the model predicted $80,000. Should I be extremely happy that the number was so high, the $100,000 sale price was so high compared to my $80,000 prediction? Or should I be not surprised? And the way to know whether you should be not surprised or surprised is to know the error associated with your prediction, know the standard deviation, know the possible distribution of outcomes that could have occurred. So if we imagine that, the mean expected value for my home price was $80,000, but the standard deviation on that price was actually $40,000, then we know the $100,000 was totally expected, totally reasonable. On the flip side, if the standard deviation was $5,000 and I sold my home price for four standard deviations away from the mean, I should be like, whoa, this was extremely unlikely and I got extremely lucky, right? So that's why it's useful to have a probability distribution as sort of this is why it's sort of useful to think about probability distributions as models as the model we're trying to learn.
Perfect. Okay. So we started off with the linear regression. We are at this point of time, I mean, in simply put, like I have a function, I give a couple of inputs, I get an output back. Now we are talking about probability distribution that, okay, I'm getting a set of outputs back with some confidence scores, which is like, okay, how much likely or how much not.
Precisely. Yeah.
Okay.
And so this is still in the realm of linear regression. It's just sort of asking more about the distribution associated with the prediction from linear regression rather than just the single valued output.
Perfect.
So in order to actually now solve this problem, to figure out what M and B should be to solve this, we're going to apply something called Bayes' theorem. And Bayes' theorem is sort of an equation that lets us relate P of Y given X and M and B to the probability distribution over the parameters of my model given the data that I have. Now, if this isn't abundantly clear from that phrasing, I've provided us a little bit of an aside to discuss what Bayes' theorem is. So I'm going to start by introducing us to the idea of conditional probabilities. That is written in this first equation here, which is the probability of A given B is equal to the probability of both events A and B occurring divided by the probability of event B occurring. In sort of plainer English terms, let's say I'm sitting at a red light and I'm watching cars go by. And one thing that I notice is, sometimes when people wait a long time at a red light, they tend to jump that red light. Mm-hmm. And I might want to start asking the question, what is the probability that someone jumps the red light given that they've waited 10 seconds at that red light? Well, that's equal to the probability that I can calculate that by saying, well, what is the probability that someone both waits 10 seconds and jumps the red light divided by the probability that they wait 10 seconds over some course of time. So that's just conditional probability in a nutshell. On the flip side of it, if I know the probability that someone jumps the red light given that they waited 10 seconds, I might also be interested in the question, what is the probability that they waited 10 seconds at that red light given that they jumped the red light? Like, let's just say I missed it. I wasn't watching what was going on. I turned my head, I saw someone jump the red light, and I want to know the probability that they waited 10 seconds.
So now you're looking at it from a different perspective.
Yeah. You're basically inverting the condition, basically.
What is the advantage of doing that? And how is it related to, if I come back to our original topic of generative AI, where does this all link together?
Good. So when we're thinking about sort of modeling, statistical phenomenon or something like this, one way in which we might start fitting our models is we might say we need our model to behave a certain way when an event is occurring.
Okay.
Right. But when we actually want to apply our model, what we need to know is we need to know that the event is occurring given that our model predicted that event occurring.
Oh, okay. So
right.
Okay, makes sense.
Yeah. So it's the difference between having like a posterior prediction, seeing how much posterior predictive power you have, and trying to just fit the model to the data.
Okay. There is a follow-up question. Is this like a chain rule of probability?
Is it like a chain rule of probability? I don't think I would say so. I think it's sort of just sort of an arithmetic result that you can kind of get out. If you just plug in, the first equation into the second equation, it kind of becomes abundantly obvious that these two things are equal. Chain rule to me has a slightly different meaning, so I wouldn't necessarily call it chain rule. Yeah. That said, we could go through this quick example here, but just kind of going through it, like one thing that if you just read this question to yourself, if you say, let's say that the SPX, the S&P 500 ticker has a 1/2 probability of going up each day and a 1/2 probability of going down each day. And maybe I'm very interested in predicting what the SPX is going to do, right? If I could do that, I would be very, very wealthy for sure. And I build a model that I find that given that the SPX will be up on each day, my algorithm predicts it'll always be up with 100% probability. But given that the SPX will be down on a given day, my model is only 50-50 accurate. So one thing I might want to be interested in is like, okay, so what is the forward predictive power of my model? That is to say that given that my model predicts down, what is the probability that the SPX predicts down? Now, I've worked out the algebra for us here. I'm not sure what many of your intuitions will be, but at least for me, when I first saw this question, before I had written everything down on a piece of pen and paper, I would have said, it's like 50-50, right? The model is only 50% accurate when the SPX goes down based on the way the problem is stated. But it turns out that there's a little bit more predictive power that I would have left on the table if I just assumed that, right? Because it turns out that when I really read carefully, the model only ever has the opportunity to predict down when the SPX is down. So if the model is producing a prediction of down and I don't know what the SPX is going to do, I should pretty much be guaranteed that the SPX is going to be down. So that's sort of like a nice sort of Bayesian result from in probability that shows that sometimes, like you can get some interesting intuition and interesting results out for models that may not look as exciting as you want them to be from the get-go. That said,
so question is like, suppose your model did not behave the way you predicted. How would you, what is the next step after that? How would you change your probability or equations or parameters? Like, how does it work?
good. So there's a good amount of complexity there in terms of how can you improve your model and things like that.
In layman's term, maybe.
Yeah. You might choose so from up till now, we've been talking about linear regression almost exclusively. You might find, okay, the model isn't doing very well, or it's doing much worse than I expected. And so you might say, I want to walk away from linear models or something like this.
Or maybe choose another model from the candidate models that you had.
Yeah. So maybe a quadratic equation or something like this, or maybe something like this. That's one way you could, what's popular nowadays is to go to deep neural nets or to transformers or something like this to solve.
Okay.
But
So
there's many other things that you can do. You can incorporate new features, new predictor variables or something like this as well. Things of that nature.
Okay. Awesome.
Yeah. So, I've set up all this, I've set up all this work, and one of the questions you might be asking now is like, well, why did you do this? What is the difference between these two things? Isn't the answer from both approaches here kind of exactly the same? And yes, it turns out that the actual answer is exactly the same, but an interpretation you might get out of it is slightly different. And so let's quickly talk about that interpretation. In the first case, we learned a model that yields a singular prediction given an input. But differently, I could say, look, this model that I could have a model that, predicts cats or dogs from a picture. And that's all it does, right? This is a discriminative model, right? All it can do is present you with discriminators or singular predictions that just kind of can be used to label data or something like this. On the other hand, when we learn a probability distribution, that's where I think we start to get towards generative models or generative machine learning, right? Because not only are we able to learn the probability distribution, we can generate new examples by drawing from the probability distribution that we have, right? And so this, I think, is where generative ML starts to differ from discriminative ML. It's the idea that you're interested in learning probability distributions that you don't necessarily think about when you're learning about discriminative ML. Now, I've said this. One thing that many of you may be thinking or maybe should be fearing is that, oh my God, is this guy telling me that linear regression is generative? And in some sense, yeah, maybe that's exactly what I'm telling you. Linear regression does generate predictions based on inputs, and it can also give you an error on those inputs, and maybe it is generative in that sense. But of course, this can't be correct, right? There's no deep neural networks here. There's none of the, everyone could have done this 40, 50 years ago. Why is it only interesting now? Is it because deep neural nets are around that I can do something like this? And well, if we explore it, I'm totally allowed to replace my linear model with a deep neural net or something like this, right? I can say instead of y hat being mx plus b plus epsilon, I can make y hat a deep neural network of x or something like this, right? Let that be a multi-layer feed-forward perceptron. Let that be an LSTM. Let that be a recurrent neural net, whatever, right? I'm totally allowed to say this. And now instead of maximizing my P of y given x given m and b, I maximize that over all the parameters of the neural network data. And that's totally allowed. But I'm still it's still kind of ridiculous to call this generative. No, it's not really a generative model. And that's totally fair. That's a totally valid complaint to have. And so what I'm going to argue is that generative AI is not so much about what makes generative AI interesting colloquially is it's about the inputs and outputs, right? So in the examples that I've shown so far, linear regression, it's single input, single output. If I had more than one variable, so let's say I wasn't just considering the square footage of a home, I was also considering the age and the number of neighboring units or something like this, I could do multilinear regression, and I could be multi-input, single output. We're looking at classification and regression problems. We're also like looking, okay, here are all the intensities and the colors of these pixels. I just want the class label though from that thing, right? That's inputs and outputs. So in each case, we're generating an output. But when we talk about generative AI colloquially, we don't think about these as being generative, right? We think about a generative model as being something where we output that is something similar to our input, right? What I mean by that is like we draw a picture based on some noisy version of that picture. That would be a generative model, right? Thinking of diffusion models here. We answer a question with text given text. That's generation via a transformer or something like this, right? The input and the output both kind of live in the same sort of space of solutions, right? And so generative AI, I think what's made it interesting in the past couple of years is the ability to model both in multiple inputs and multiple outputs at the same time. And that's sort of what makes it really, really exciting and really different from the flavors of machine learning that we've had so far. In order to do that, of course, we need to start thinking about modeling probability distributions, as I've kind of described thus far.
So question over here is, how exactly does a GPT model implement probability? The same input token sequence to a GPT will always output the same output next token, unless selection is manipulated by temperature, etc.
Yeah,
is that even correct?
So
if the temperature is 0, will it always give you the same answer?
Yeah, so the zero temperature limit is exactly the limit where things become fully deterministic. I don't think people typically train in this limit. They don't usually train in this limit because what they're trying to do is they're trying to match the distribution of outputs they're trying to match the distribution of outputs to some supervised label or something like this. And so there may be many possible examples of like, what should the next word be given I have a? There may be many possible examples over the course of my entire corpus of text or something like this. So your outputs should be some distribution of dog, cat, bird, car, something like this. And what the zero temperature limit does is it chooses the highest probability of those next outputs. Any single one of those outputs is totally valid and totally reasonable.
Is it even possible that if for example in this context, if dog is the highest probable, and if I set it to 0, is it even possible that next time I try it, or if I try it nth time, I'll get cat?
Yeah. So if you set it if you take it in that zero temperature limit, you are always choosing the most probable predicted token,
unless the model is updated with some other weights or something like that.
Yes, right. If the model okay, good. Assuming the model is held fixed, it'll always predict the same thing. But typically, I think people don't even want to generate in that limit because you do want some diversity in the result that you generate.
But then going back to the question, how exactly does a GPT model implement probability? Did we answer the question? I'm just making sure.
Yeah. So the way to think about how a GPT model implements probability is by predicting a set of probabilities over the possible tokens that can fill in the next blank or something like this. If you're doing next sentence prediction or something like this, right? It predicts out the set of probabilities. And what you'd like it to do is you'd like to try and match that probability distribution to the probability distribution that exists in the corpus of data. So it will. So if you're kind of super technically inclined, like that last layer of a GPT is usually a softmax or something like that. Actually, not 100% for the softmax. I'm super familiar with the softmax setting for transformers and things like this, but it's usually a softmax, which is basically outputting probabilities over tokens to decide what to fill in. And so you can basically want to match that final probability to the real probability in the data set.
So GPTs would be better in math computation if they were trained to be purely deterministic. Next question from Maria.
That's an interesting question.
That's an interesting question.
Yeah, that is a very interesting question.
Because typically GPTs are not. That's what we know, right?
Good. Yeah.
I
So
like-
as
I mean-
understood it, GPTs are not trained in the zero temperature limit typically.
No, I mean, what I heard or what I read is like GPTs. I mean, GPT can do maths, but GPT is not great in doing maths, right? I mean, I might have a calculator can do maths faster than GPT would do, or
Yeah,
more
so
accurately.
I think the other strong constraint here is that like GPTs are not explicitly trained to do math. They're explicitly trained to do next sentence prediction. And there's plenty of like, or actually there's plenty of ways to train GPT, but like, or an LLM in general, right? But because you have all these other competing factors and like what is plausible English language or something like this, that like being wrong in a particular math problem or something like that may not be as punishing as having poor grammatical structure or something like that in your output. And so I think the real solution to get a model to really know how to do math very, very well is to either like directly inject proper mathematical rules in as a part of the architecture of the model that you're interested in which case you're starting to recover a calculator or something like this, or to only train it on, rigorously correct theorems and things like this, in some like logical symbolic representation where
The question would be like, why would I even use GPT for a math problem, which is a probabilistic, right? Math is a deterministic thing.
Well, good. So there's actually like some really interesting papers that are coming out of Google and Microsoft nowadays on like how can you use LLMs to propose lots of different mathematical proofs for the same concept, or in particular the one example I was looking at is like proposing lots of mathematical functions to optimize a particular objective or something like this. And the probabilistic outputs lets you test lots of different candidate solutions in sort of like a rapid time frame. And they might actually like pursue sort of solutions that are not typically like thought of as being correct. I mean, you can even think about this in terms of chess, right? Like chess is like, for as complex of a game as it is, like there probably is an objectively correct move in like many, many instances, but it is useful to have a probabilistic system because you can't fully and analytically solve out all of chess, at least with current computers in finite time, right? It would take an infinite amount of time to calculate all of that depth in chess. So I think there's like, it is sometimes useful to have probability distributions as outputs and like pursue those outputs with some amount of probability, just so you can like kind of sample from like, here are possible different approaches to the same problem or something like this.
Okay. Can you also, I think, Aaron, you shared a nice link, so definitely we'll check it out, mathgpt.org. Equal to unlimited. So that's, can you also touch base on autoregressive models, right? So what does it really mean? How is it connected?
Good. So in an autoregressive model, what you're effectively doing is you're saying, I'm going to like, let's say I have the first K time points in a time series. I want to predict the K plus 1th time point, right? And then I'm going to advance forward by saying, okay, now I have the first K plus 1 time points in some time series, and I'm going to predict the K plus 2 time point. And I'm going to keep iteratively doing this. In sort of a language setting, that's like basically me saying like, I am going to start from nothing and I'm going to predict what the first word of most sentences are. That might be I, or that might be the, or something like this. And then once I have the first word of the sentence, I'm going to predict the second word. Once I have the second word of the sentence, I'm going to, based on the first 2 words, I'm going to predict the third word. Then I'm going to predict the fourth word given the first 3 words, and so on. So this is an autoregressive model or something like this. And this is a particular so optimizing autoregressive models are really nice because you can get lots of supervised examples very quickly from a given data set, right? Like I only need a couple of sentences. And then once I have a couple of sentences, I have so many examples of like, okay, what's the next word given the first N words or something like this.
How is autoregressive models different? I mean, like, definitely it is another model, but then how is it related? So we, as part of this discussion, right, we started with linear regression, probability distribution. Then you walked us through the Bayesian approach as well as the Bayes theorem. Then we are talking about like generative AI. Where does autoregressive fit in?
Good. So, let's circle back to the very beginning of the conversation where we talked about what X and Y are. So X was a predictor variable and Y was a response variable.
Mhm.
An autoregressive model is a flavor of model where X is the first N words of the sentence and Y is the next word in that sentence.
Perfect.
Right. So this kind of like these kinds of autoregressive models, and it's all about like what your X and Y are really being chosen to be. That's what really that's what really differentiates that model from any other flavor of model.
Okay.
Yeah.
So, in one of the podcasts that I was listening to from Lex Friedman's podcast, which is by Jan LeCun, right? So they were saying that generative AI is great, but then in order for us to go to the real artificial machine intelligence or AMI or AGI, these autoregressive LLMs are not going to be enough to take us to that next level. So if you can just touch base a little bit on that one, what does it really mean?
Yeah. So I can't. So I think what Jan LeCun is starting to point out there is that there are plenty of issues that exist in today's space of AI model, right? In sort of the generative pre-trained transformer land and the large language model land. And one of which is that these models require billions and billions of parameters to do the computations that they're doing. And you compare them to the intelligence that even like most animals and most humans have, and that's done with significantly fewer parameters and with a significantly smaller energy restriction and energy constraint. In addition, like humans are much more capable of generalizing, compared to sort of deep, and compared to some of these deep neural nets and compared to some of these LLMs and things like that, right? And so what I think Jan LeCun is kind of getting at here is that there are all sorts of rules, physical rules that exist in nature that constrain the possible outcomes that you should be, that can occur. And part of intelligence is to know what possible outcomes are reasonable when you're giving back a response, right? You don't necessarily just want to index on what is statistically likely, because there may be things that are statistically unlikely to occur, but are totally valid. And so in order to kind of predict those things that are statistically unlikely, but totally valid, it's useful to know the physical rules associated, that are existent in the universe. I can't fully read his mind or anything like that. I don't know exactly what Jan LeCun is thinking, but I think the other side of it is also being able to do these kinds of computations without requiring insane amounts of electricity or something like this, right? Like humans have 2,000 to 3,000 calories a day that they consume, kilocalories, whatever. That's much less than what it costs to run OpenAI's ChatGPT or Anthropic's Claude or something like this. So asking sort of how you can do that kind of thing is also quite interesting and probably a necessary step in making the next big advance in machine learning.
Okay.
Yeah.
Sounds good. I just want to make sure like I did not derail you from your train of
All
thought.
good.
All good.
Okay. Cool. So I think with all this said, I think I kind of do want to jump into sort of a specific example of a generative model, and I'm going to show one that was kind of introduced in sort of like 15 or 16 by Kingma and Welling. Yeah, it's called a variational autoencoder. And so I'll start by saying, look, we've established now that generative AI is really about multi-input, multi-output. That's what makes it really, really interesting and exciting. So let's try and figure out what one such example should look like. And I'm going to propose that the way we're going to do this is, well, like if I walk up to a painter or an artist or something like this, and I told them, hey, I would like a picture of a cat, a dog, and I want it to be mostly green, they could take those three specifications and produce you a very, very nice picture, right? Produce you some really, really pretty picture. You could also give them, I actually want no cats, but I do want a dog and I want it to be mostly blue instead of mostly green this time. That's a different set of specifications, which they could then take in and generate another interesting example. Is it possible to get a machine learning model to do the same kind of thing? And in practice, what this is asking us to do is to say, look, what we'd like to do is learn the probability distribution of some set of images, given the specifications that I've been asked, right? Because there are many possible ways to achieve that picture of a cat that is mostly blue or something like that, or a picture of a dog that is mostly green, or pictures of cats and dogs that are mostly red or something like this, right? So I'd really like to learn that probably the map that takes us from the specifications that I provided to a possible set of images that I could be working with. So kind of visually, the way to think about this is imagine I have some set of input nodes. That's going to be the Z layer that specifies some underlying control knobs that I really want to tune, and use those control knobs to push out some output that is like, human interpretable and that a human would call a picture or something like that. How can I actually train a model like this? Well, I can train a model by applying Bayes' theorem, right? So we said we wanted to set out by learning P of X given Z, but I know from Bayes' theorem, I can turn this into a problem of learning P of Z given X, right? Learn the probability distribution of my underlying control parameters given a set of images. Now, if I have a bunch of examples of pictures, one thing I can say is, look, the first thing that I've done here is I've turned my small input, multi-output problem into a multi-input, small output problem, kind of recovering that flavor of machine learning that we were talking about when we were talking about discriminative ML for the very first time, right? That's sort of very simple machine learning, very simple set of linear regression type problems I can think about. And of course, in order to learn P of Z given X, I can approximate it with a neural network that I'll call Q sub phi, right? Q sub phi of Z given X. In order for me to do this though, I need to know the probability distribution of the images, right? And what this is going to be is just going to be my empirical data distribution, right?
Okay.
I've sampled a bunch of activity.
So sorry for stopping you with that.
No, go ahead.
Quick question. So you always say that, okay, I replace it with a neural network. Can you explain that sentence a little bit?
So P of Z given X is some function, right? It's some function that we don't really know about. We don't know what it looks like. We don't know what it should be, but we need some way of approximating that function. The power of a neural net in any meaningful capacity is to approximate all functions. If you sit down and you read the universal approximation theorem or something like this, it proposes that a sufficiently wide feed forward network can approximate any function. And so when I say, we're gonna approximate P of Z given X with a neural network Q of Z given Q phi of Z given X, what I'm basically saying is like, I don't know what P of Z given X should look like, but I bet you I can get close to it if I use a sufficiently parameterized neural network.
Okay.
That's what I mean here.
Okay. Awesome.
So we're going to have some empirical data, right? I've collected a bunch of images off of Google or something like this of cats and dogs and colors and things like this. And that's going to be my P of X. And I also have some unknown distribution, which is what should the distribution of latent variables look like? Now, in general, this is not an easy question or a tractable question to solve, but for variational autoencoders, you typically take a guess. You take a guess at what that distribution should be. And in the variational autoencoder world, what was chosen was that P of Z should be approximately Gaussian with unit covariance, which is to say, I'm going to say it's described by a bunch of Gaussian random variables that are unrelated. Why is this useful? I'll show you in just a second. Before we hop into it in too much detail, kind of going back to that sort of visual world, basically what this network has become, which was initially just Z to X, right? Going from Z and decoding into X, it's actually become, I have some X, I have some set of images that I'm encoding into some set of underlying variables Z, which is many fewer than the total number of pixels in my images X, right? Then from that very small set of numbers, I'm going to generate back a bunch of pixels that I'm really excited about, or something like this, like a new example of that image. And that's going to be the decoder piece. So the right-hand piece of my, of the network that I've drawn for us here.
Can you give another example, which is like more real life so that people can relate to? Possible?
Sure. I think, we'll get to in the next slide, I'll show you sort of,
okay. Yeah.
I'll show you an example.
Right.
But before we hop into it, what is like optimizing this involves optimizing some objective function. And that objective function is basically first, we want to make it so that our encoder is as close to matching what we expect the latent variables to look like. That's that first term in this equation. And then our decoder is doing as good a job as possible as using those latent variables, those Z's, to predict out an outcome that looks somewhat realistic. Here, realism is based on reconstruction of the original input, right? How much does it look like what I originally put in? Note that X will never look exactly like Z because it's being passed through this really tight bottleneck. We're going to lose some information in that compressive step. And so X can't, the output can't ever be guaranteed to look like the input unless your model is deeply overfit. Cool. So you would ask for an example. You would ask for exactly what am I saying when I say all of these things? Well, imagine now, if you're not familiar with MNIST is the, standard handwritten digits that everyone tries to write their classifier on for the first time or something like this. If I look at something like MNIST, and I train a variational autoencoder on MNIST, one thing that I see is, okay, I take this image of 784 pixels and I project it down to this 2-dimensional latent space. Now, one thing that I immediately observe is that all of the 9s sort of cluster together in this bright green patch, right? All of the 0s cluster together in this sort of blue patch over here. All of the 6s cluster together in this brown patch, right? What's nice about that is now when I want to generate a new example of a 9 or a new example of a 6 or a new example of a 2 or something like that, I know that if I go and specify that point in latent space and choose those to be my Zs, when I use my decoder, I'm going to get something that looks like a new example of a 6, a 9, a 2, or whatever, right? Latent space has enabled me to kind of control what I'm outputting a little bit. And that's sort of what we're looking for. That's sort of what we're looking for when we encode from images to latent space and then decode from latent space back to images. I borrowed this figure from Kaggle for the record. I didn't train a variational autoencoder on MNIST, but I will show you some examples of variational autoencoders I have trained in just a second. Does this answer the question that you were asking initially?
Yeah, I think it definitely gives some context. Yep.
Perfect. So thus far, we've talked a lot about image generation. There have been lots of questions about text generation, things like that. But there's also a lot of excitement and interest in using these sorts of generative models in biology and in and in many forms of science, really. And so I come from a biotech background, and one of the things that people have talked about a lot in my field is how can we use generative ML to generate new examples of proteins or something like this.
Mm-hmm.
And so one modeling approach that people have taken is if you train a variational autoencoder on a bunch of natural protein sequences that you can pull out from existing databases from the academic sphere or something like this, can you use that model to predict novel synthetic proteins that actually function? And here there's some technicalities that I've described, but one kind of key driver behind doing this is that, we talked about this latent space as being, sort of a way in which I can pick what I generate or something like this. One thing that would be really nice is like, okay, if I have a protein that does something and I want to change its function slightly, can I very carefully and very cleverly choose a point in latent space that gives me back the right version of that protein? Right?
So
Does it give me slightly different behavior?
Rather than questions, point over here is like what you're saying is typically in the industry, where I belong, everyone is talking about generative AI and also like reading documents, searching and summarizing, text completion. But you're saying generative AI is also heavily used in biology and like artificial intelligence also. And that is the area that you work on.
Yes, correct.
So the next thing that you're saying is, as you mentioned earlier in latent space, and based on like how I understood latent space is in layman's term, it's like if I have a big party with different people in different colored clothing, so you're trying to group those colored clothing into one single space, right? So like kind of like the the picture that you showed, right? The red over here and the green over here, like. So I was visually thinking it as a room full of people with different color codes, right?
Yeah.
Clothing, right? So that's what. So now you're taking this concept and implementing it in protein synthesis as well.
Yeah. So I think one thing I want to hammer home here is like, it's not, the grouping is really, really nice, but in your example, one thing I'd like to do is I'd like to generate a new example of that clothing with that kind of color that is different.
Yeah, that is the part I missed. Okay.
Yeah.
Got it. So not only you took a bunch of examples, you grouped them together.
Mm-hmm.
Now
But
you're
because
also
I know where they group. Yeah. Good.
Now you're also generating, and then it belongs to that.
Precisely. Right.
Okay.
So by selecting a point from the right group that isn't observed in the data set, I can generate something that looks like it belongs to that group.
Correct. Okay. A couple of points over here. I think,
Mhm.
Marian, you have some good points. So let me quickly read it out and then we can go back to the topic. So I think math.org, mathgpt.org. Okay. So going back to our initial topic of like can I use mathematics for GPT? Like, can I use GPT for mathematics? So what the point over here is like Math GPT is using agents, a Python calculator to produce math addition accurately. So it's like a mix hybrid, right? In this case, like it's not only the LLMs and the GPTs, but also it's using some Python calculator. So that's good.
Mhm.
Mythic analog matrix multipliers probably can do the GPT matrix multiplication part, but the company is focused on image examination at the edge. I didn't follow 100%. Vedant, any comments over here?
So totally makes sense to me that there is some
Okay.
in the first example that there is some fact checking that is being done by like a ground truth calculator or something like this. I think
Okay.
this is kind of consistent with what I think was initially proposed, that you need to build in some physical rules into your model, and how you achieve those physical rules, whether you have a validator, which is that sort of Python calculator or something like that. That is sort of an open question. I'm not quite sure what is meant by the second comment. Is this just saying like, are you trying to say like, how could I discover a new algorithm for doing matrix multiplication or something like this?
I'll speak because I can't type fast enough.
Yeah, no
Mythic
problem.
built an IC that has analog matrix multiplication using, for example, flash memory as the memory to determine the weights in the system, and then the current sent through the matrix of flash memory generates a current. The voltage into the memory generates a current which is summed that produces the multiplication. So they're able to multiply using analog voltage and current. In what they've done is they've made a module that has like a RISC processor and a network. So they can string together a bunch of these matrix multiplications to do on some scale, matrix multiplication at like 1/30th of the power consumption of a GPU. But they don't have any circuits that can perform the full GPT stack of levels and things like that. So as far as I know,
Yeah.
but the question of power consumption came up, and I know that is one solution that has potential.
Got it. Okay. No, I see the context now. Yeah, that's super cool. That's a very cool approach to doing sort of matrix multiplication. I wonder if the challenge there is that when you need to scale it up to the size of a GPT model or something like that, like the actual, like, I wonder if you start to, like, in order to get it to fit into a reasonable amount of space, you start to face like Moore's law or something like this, right? Like,
They had trouble fitting in the multiplexer, demultiplexer, and analog to digital converters on the IC. So there's some technical challenges
There's
in
some
building
hardware
the
problems.
size of the matrix multiplication.
Mm-hmm. No. I think that tracks me. I don't know much about electrical engineering, but I could guess that the size of the circuit starts to grow very, very large.
And the last point that you have is it is imaginable that a large GPT trained on human DNA could determine and output the DNA sequence that provides phenotypes X, Y, and Z.
Yeah, so I think a lot of people are really. NVIDIA has BioNemo, which is supposed to be something like this. There's lots. There's the Ross Lab, which has another similar model. There's a lot of biotech companies that are either building or have built, as well as lots of academic labs that have built these sorts of LLMs that are trained on all of the DNA that is observed out there, or all of the protein sequences that are observed out there. This is definitely like something that is quite exciting for a lot of people, and it's just a question of like, does it work? And I think that's been an open challenge for a lot of these biotech companies. So, the first one to make it work will certainly earn a lot of money and win a lot of awards for their progress in medicine and things like this. But I think we're not quite there yet. Whether it's 3 months away or 3 years away, this I don't.
So coming back to your topic, sorry, I kind of like stopped you and then digressed, but then we are back on top.
No, absolutely.
And also
So
we are
I
at
think-
time, so maybe like if you can wrap it up, and then part 2, 3, 4, we have a lot more to unpack.
Goodness. What I was just going to leave you with was a flavor of like, okay, so, we were talking a little bit about various model encoders as generative in biology or something like this as one sort of example of a generative model. What I'm showing you here is some data from a VE that I did train. that basically separates this particular class of proteases on the specificity for the thing that they bind or something. There's the thing that they cut. And one question you might ask is like, oh yeah, the chymotrypsins are all blue and they're right next to each other, and all the trypsins are all orange and they're right next to each other. What if I wanted a serine protease that kind of that was a chymotrypsin, but looked more like a trypsin in some way or something like this? By cleverly selecting a point in latent space and then generating from that point, can I get a reasonable example? That is sort of one thing that I think is an interesting application of variational autoencoders that people have been pursuing for some time, that people are sort of interested in. With all that said, I'm just about ready to conclude anyway, which is what I hope to have given you today is a little bit of intuition for what I think is the major advance of generative ML. At least this is, my opinion for sure. But I think what makes it interesting is that we're going from a world where we only we took high dimensional data in to model low dimensional outputs, to a world where we can take in high dimensional data and model high dimensional output. I think that's really what makes generative ML in its current form really exciting and really different from the flavors of machine learning that we've seen in the past. And I also hope what I've shown you is this Bayesian approach and this Bayesian style of thinking can enable us to turn really intractable problems, right? Modeling high dimensional outputs from low dimensional inputs into a more tractable problem that we are more familiar with. That is, modeling a low dimensional output from a high dimensional output. This idea is sort of what gave, I think enables some of this, enables at least variational autoencoders to be somewhat sensible for most of us. There's lots of remaining questions. Go ahead.
This was fantastic. We are at time, so there is one point over here, Marin. DNA sequence synthesis. So AGI GPT connected with a CRISPR lab machine and a sperm bank milling system could simply build smarter or obedient humans to provide it with electricity and defend it politically. Oh, that's an amazing point of view. Go ahead, Vedant.
Hang on, I'm reading this now. Connected with a CRISPR lab machine and a sperm bank.
That's amazing.
Terrified of that reality. I would gamble that we're very, very far from that reality. So, good for our independence for sure, for at least a little while.
Yeah. Go back to the Matrix, movie. I think this was amazing. I'm pretty sure the other people in this group enjoyed as well. But what you did was like you gave me a lot of homework to do, because you ignited a lot of questions in my mind. I'm going to do a lot of Google until we meet 2 weeks from now. So thank you, Vedant, for your time.
Absolutely. Hopefully this was interesting and gave some flavor.
I have a question now. And actually, I'm more in the data engineering point of view developer, but I'm recently coming to the generative AI space. So I'm good in some kind of ML stuff like a linear regression. I build a couple of model monitoring stuff and serving stuff. So how I can get the more knowledge, especially the understanding of the neural network, these things. What kind of suggestions you are going to, like a kind of I'm new to this area, especially generative AI stuff. I mean, generative, I'm assuming like it's like a more API driven, the vector embedded, it's more my skill set is data point of view, I'm just making it. But neural network space, how can I start and where can I start?
Would you like me to give an answer, Joel, or are you?
No, go ahead. You're the expert over here.
So I think good. So, okay. I'll start by saying the reason I set up this conversation this way is because I think it is very useful to set up our understanding and our intuition behind the models we use from a place that we understand extremely well. That said, when you want to build these familiarity with these new models and things like that, there's plenty of good. My approach has been to almost like copy and paste or type out, like take an example of an existing model from an academic paper or an academic lab and type it out myself by hand, like each line by line, to see what's going into it. And if I can reproduce the results of a paper or something like this, some small version of it thereof, I can generally get some good intuition for what's going on. The actual mathematical intuition behind what's going on in these models, I would encourage you to look into sort of variational inference type papers and things like this that are useful for understanding sort of the underlying math behind the way some of these models work.
I'll also add on top of what Vedant said. So Vedant came from a PhD scholar perspective, right? I'll give you a architecture, implementation, or a development perspective, right? So, and in layman's term, it's like there are two parts of it. And Vedant, correct me if I go wrong at any point of time. So there are two parts of this whole game that I understand. One is a consumer, and one is a producer. So someone is producing models, and most of the 90% of the population, the projects that we are doing are consumer of those models. So I'm using GPT to build applications. I'm using AI to so for example, Snowflake just came out with a
New model.
layer called Cortex, and then Arctic is their LLM, new LLM, right? So basically, from a data standpoint, what I'm thinking, like again, it can be like different perspectives, but what I'm thinking is from a data standpoint, what we want to do is like, okay, I am a data engineer. I understand data. I understand Snowflake. What is Snowflake building? Like what kind of LLM they're building? What kind of applications they're building? So that is one way of looking at it. If you want to flip the coin and go to the other side where Vedant exists, right? So he's coming from a research scholar, papers, and building machine learning. So if you are interested in that area, then you have to take a different route. But it was my perspective. Like,
I might be able to add to something here. I
Yeah.
couldn't understand every word of the gentleman. His Indian accent was thick, but he wants to learn about neural nets. I've been using ChatGPT and its peers like Gemini Pro to write neural net in Python that would included pre-training a training system. So I used that to write a 2-input XOR gate, a logic gate, and then train it to generate an outcome of either 1 or 0. But I heard that you could use a neural net to implement a multiple input Boolean thing, and I have not had success with that. It doesn't train. I can't get it to train to output a Boolean. So that's a challenge. You can ask GPT to help you, to tutor you in neural nets. It'll write Python code to implement a neural net with training, and then you could look up how other people have solved it, and you'll see that it'll teach you how to do back propagation and choose your loss and things like that. And so I've gotten like baby steps towards figuring out how to build a GPT in that way.
Oh, that's amazing. That's interesting. So maybe like Marian, at some point of time, you can do a presentation and show us like.
Thank you, Maria. Definitely. Yeah.
And also, I've used GPT to write these chat with PDF files. Okay, so I already showed you in the chat, Hugging Face chat with PDF. So I didn't find the startup Python examples in Google to be very helpful. So I used maybe a combination of Bing, ChatGPT, and Gemini to produce a chat with PDF. So I gave you a link. Here it is again. So yep. I can't write in Python. I can't write from scratch in any programming language, but I can debug it. So therefore, with the help of Gemini or ChatGPT, I can write hundreds of lines of code that work eventually. So I wrote this with Gemini, and it uses the free Gemini API. And it would be trivial to add the chat with images function into that, but I didn't get to that because I didn't need it. But I'm not a coder, but I can write 300 lines of
So now we have all
chat.
Power. Yeah. Just like we have infinite memory with Google Photos. Okay, being said that, I think we'll wrap up 7-11. Thank you. I think this was very interesting discussion. We had a lot of interactive topics back and forth, and until 2 weeks from now, once we meet again. So good night, everyone. Have a nice evening.
Thank you. Yep.
No, yeah.
Thank you. Bye.
Thank you.